Right now, as you hear these words, a star is being born in the depths of space. And while it takes its first breath, somewhere in another galaxy, another dies, exploding with such force that its light will travel toward us for billions of years, yet never reach Earth. In 1 second, about 4,000 new stars appear in the universe. 4,000 every second. And this number is so unimaginably small compared to what already exists that your mind simply refuses to accept it. We are used to thinking that we know space. We have seen beautiful photographs of nebulae, read about black holes, and heard about the expansion of the universe. But there is one simple question that can destroy all our self-conceit. How many stars actually exist? Not approximately, not about, but truly. How many are there in this abyss we call space? And when scientists finally tried to honestly answer this question, they faced something that made them fall silent, because the answer turned out to be not just a large number, it turned out to be a sentence to our ego, our significance, our place in the universe. Today you will learn 3 things that will change your perception of reality forever. First, why official estimates of the number of stars are underestimated by hundreds of times and what this means for our understanding of space. Second, what monstrous forces hide behind every glowing dot in the night sky and why most of them are capable of destroying all life within a radius of tens of light years. Third, what happens in those parts of the universe that we will never see, and why the very concept of the observable space is only a tiny window into the infinity that we cannot even imagine. By the end of this journey, you will understand something important, something that will not let you sleep peacefully. Because when you realize the true scale of the stellar population of the universe, you will understand that we are not even a speck of dust. We are a statistical error in an equation of such size that the very term infinity begins to seem insufficient. If the mysteries of space fascinate you, if you are ready to look beyond the edge of the familiar, subscribe to the channel. The journey begins right now. Let us start with what we are told in school, with that version of reality that we take for granted without asking extra questions. We are told that our galaxy, the Milky Way, contains from 100 to 400 billion stars. This is the official estimate that can be found in any astronomy textbook, in any encyclopedia, in any popular science film. 100 billion stars. Sounds impressive, right? This is a number with 11 zeros. 100,000 million glowing balls of incandescent plasma, each of which is a thermonuclear reactor of colossal size. And then we are told that there are about 2 trillion such galaxies as our Milky Way in the universe. 2 trillion galaxies. This is a number with 12 zeros. If you multiply 100 billion stars by 2 trillion galaxies, you get about 200 sextillion stars, a 2 with 23 zeros. This is the official estimate of the total number of stars in the observable universe. 200 sextillion. This number is so huge that the human brain is physically incapable of comprehending it. We can write it down, we can pronounce it, but imagine it? No. Our brain evolved to count to several dozen, at most to several hundred. Everything more is just a lot for us. And here, the first lie begins. This estimate of 200 sextillion is based on what we can observe, on what our telescopes are capable of detecting, on that light that has reached us in 13,800,000,000 years, the age of the observable universe. But the observable universe is not the whole universe. It is only a tiny bubble of reality around us, limited by the speed of light and time. Imagine an ant sitting on the surface of a balloon. It can see only a small patch of rubber around itself. For it, this patch is the whole world. But the balloon continues beyond its vision. And here is the scariest part. The balloon is constantly inflating. The boundaries of the visible world for the ant are expanding, but the balloon itself is expanding even faster. There are parts of the balloon that the ant will never see because they move away from it faster than light is able to overcome this distance. We are this ant. The observable universe is our tiny patch of rubber. And the real universe, it can be billions of times larger or trillions or infinite. We simply do not know and, most likely, will never know. This means that the real number of stars in the universe may be not 200 sextillion, but infinity. A true mathematical infinity. A number that has no end. A number before which any of our attempts at counting look like child's play. But let us stay within the framework of the observable universe for now. Let us take these 200 sextillion as a starting point. Even this number hides a horror that we are only beginning to realize. You see, the problem is in how we count stars. We cannot count them one by one. It is physically impossible. Instead, astronomers use the method of extrapolation. They take a small patch of sky, count the stars in it, and then multiply by the total area of the celestial sphere. It is as if you took a handful of sand from a beach, counted the grains of sand in this handful, and then multiplied by the area of the whole beach. The problem is that the beach is not uniform. In some places the sand is fine, in others coarse. In some places it is tightly packed, in others loose. In the same way, the universe is not uniform. There are regions with a high density of stars, galactic nuclei, star clusters. And there are regions almost empty, voids, cosmic wastelands hundreds of millions of light years in size. When astronomers made their first counts, they used telescopes that could see only the brightest stars. Red dwarfs, the most common type of stars in the universe, remained invisible. These small, dim stars make up about 70% of the entire stellar population, but they are so weak that even the red dwarfs closest to us are barely distinguishable in the most powerful telescopes. In 2012, a group of astronomers from Yale University conducted a large-scale study. They used the latest infrared telescopes capable of detecting the radiation of red dwarfs, and the results were shocking. It turned out that in elliptical galaxies, there are 20 times more red dwarfs than previously thought. Not by 20%, but 20 times. This meant that the total number of stars in the universe had to be revised, sharply increased. But even this study took into account only those red dwarfs that could at least theoretically be detected. And yet there are also brown dwarfs, objects on the boundary between stars and planets. They are too small to maintain a thermonuclear reaction, but still radiate heat from compression. Their number remains a mystery. According to some estimates, there may be more brown dwarfs than ordinary stars. And so we come to the first destructive conclusion. All our estimates of the number of stars are a minimum value. This is the lower boundary. The real number is almost certainly higher, possibly significantly higher. And we do not know exactly how much. We literally have no idea how many stars exist in reality. But wait, it gets worse. Remember, I said that we observe light traveling to us for billions of years. This means that we see the past. When an astronomer looks at a distant galaxy, he sees it as it was billions of years ago. The stars he observes may no longer exist. They exploded, collapsed, turned into white dwarfs or black holes, and new stars born during this time have not yet had time to send us their light. The universe we see is not the real universe. It is a photograph taken billions of years ago, blurry, incomplete, distorted by time. The real universe, the one that exists right now, in this very moment, is inaccessible to us. We can only guess about it, build models, make assumptions, but see it as it is now. Never. This leads us to a paradox that is rarely discussed in popular science films. The number of stars we counted is the number of stars in the past. Not in the present, in the past. And since we see different parts of the universe in different moments of the past, close galaxies almost in the present and distant ones in deep antiquity, we are dealing with a temporal salad, a mixture of different eras. It is as if you were looking at a city and simultaneously seeing modern skyscrapers, medieval castles, and prehistoric caves, all in one frame, only on a scale of billions of years. Official science tells us 200 sextillion stars. But now you understand how conditional this number is. It is based on incomplete data, outdated observations, and fundamental limitations of our instruments. The real number can be times, tens of times, hundreds of times more, and this is only the observable universe, but reality is much, much darker. In 2003, the Hubble Space Telescope pointed its lens at a patch of sky the size of a pinhead, an absolutely dark patch where it was thought nothing was there. The telescope collected light for 11 days, almost 2 weeks of continuous observation of a tiny dot in space. When scientists processed the obtained data, they were speechless. On this tiny patch with an area of less than 1/13 millionth part of the entire sky, about 10,000 galaxies were discovered. Not stars, galaxies, each of which contains hundreds of billions of stars. This image was named Hubble Ultra Deep Field, and it changed everything we thought about the universe. It turned out that where we saw emptiness, there are actually myriads of galaxies, just too distant and dim for our usual gaze. If we extrapolate this result to the whole sky, we get about 200 billion galaxies in the observable universe. But in 2016, a group of astronomers led by Christopher Consolis from the University of Nottingham conducted an even deeper analysis. Using mathematical models and data on the distribution of galaxies, they came to the conclusion that the real number of galaxies is at least 2 trillion, 10 times more than previously thought. 2 trillion galaxies and in each hundreds of billions of stars. Multiply these numbers. The result exceeds any attempts at comprehension. But even that is not all. Consolis's research revealed something even more disturbing. It turned out that 90% of galaxies in the observable universe are too distant and too dim for us to see them, even with the help of the most powerful telescopes. We literally do not see 90% of what is within reach of light. This means that everything we know about the universe, all our maps, all our catalogs, all our discoveries, is only the tip of the iceberg, 10% of the visible part, and beneath the surface hides an abyss that we can only guess about. And here the real horror begins. Every star is not just a glowing dot in the sky, it is a thermonuclear hell. It is a place where matter exists in states unthinkable on Earth. In the center of an ordinary star, like the Sun, the temperature reaches 15 million degrees. The pressure is 260 billion times higher than Earth's atmospheric pressure. Every second, 600 million tons of hydrogen turn into helium, releasing energy equivalent to the explosion of 100 billion megaton nuclear bombs. And this is an ordinary star, average, unremarkable. Now imagine that there are sextillions of such stars. Each of them is a bomb that is constantly exploding. Each of them throws streams of radiation, charged particles, deadly radiation into space. Space, which seems so peaceful and quiet to us in night photographs, is actually an arena of incessant violence, nuclear violence on a scale before which all the wars of humanity look like children's play in a sandbox. We live in hell, a beautiful hell, illuminated by trillions of thermonuclear explosions. And every time you look at the night sky and admire the stars, you are looking at an infinite field of fire and destruction. But reality is even gloomier than you think. When we talk about stars, we usually imagine something like the sun, a yellow ball radiating light and heat. But that is as if you judge the whole animal world by one domestic cat. Stars are so diverse, so different from each other, that the very word star becomes almost meaningless. It unites objects that differ from each other millions of times in mass, billions of times in luminosity, thousands of times in size. Astronomers have developed a system of stellar classification based on their temperature and spectral characteristics. Letters O, B, A, F, G, K, M, from the hottest to the coldest. The Sun belongs to Class G, a yellow dwarf with a surface temperature of about 5,700 degrees. This is a middle-class star, not particularly standout, a mediocre one of cosmic proportions. But at the top of this classification are monsters, Class O stars, blue giants with a surface temperature of over 30,000 degrees. They are so hot that their light is shifted into the ultraviolet part of the spectrum. The human eye perceives them as bluish-white, but in fact most of their radiation is outside the visible range. These stars live fast and die young, only a few million years before exploding as supernovae. For comparison, the Sun will live about 10 billion years. A blue giant burns out hundreds of times faster. And here is what is important to understand. These blue giants are a rarity. They make up less than 1% of all stars, but it is they that are visible best of all. When you look at the night sky and see bright stars, most of them belong to these rare, powerful classes. Dim red dwarfs, which make up the vast majority of the stellar population, are almost invisible to the naked eye. This creates a monstrous distortion of our perception. We see exceptions and take them for rules. We look at the sky and think we understand stars, although we see only a tiny atypical sample. The real universe is a kingdom of dim, cold, invisible lights flickering in the infinite darkness, not majestic blue titans, but humble red dwarves, each of which shines thousands of times weaker than our Sun. Proxima Centauri, the star closest to us after the Sun, is only 4 2/10 light-years away. Light covers this distance in 4 years and 3 months. By cosmic standards, it is within arm's reach. But Proxima Centauri is a red dwarf. Its luminosity is about 16 thousandths of the luminosity of the Sun. It is so dim that it is invisible to the naked eye, despite being our closest stellar neighbor. Now think about it. If the star closest to us is invisible without a telescope, how many more stars are hiding in the darkness? How many red dwarfs are hiding in interstellar space, too dim for our eyes and even for our instruments? At the opposite end of the size scale are objects capable of tearing your imagination. Hypergiant stars, the rarest of the rare, giants among giants. Take, for example, a star named Stephenson 218. It is located in the constellation Scutum at a distance of about 20,000 light-years from Earth. Its radius exceeds the radius of the Sun by more than 2,150 times. Try to comprehend this. If Stephenson 218 were placed in the position of the Sun, its surface would swallow not only the Earth, not only Mars, not only Jupiter and Saturn. It would go far beyond the orbit of Saturn. Billions of suns would fit inside this star. And this is not an exaggeration, it is a mathematical fact. But even such a monster is a speck of dust against the background of a galaxy, and a galaxy is a speck against the background of a cluster of galaxies, and a cluster is a speck against the background of a supercluster. The scales layer on top of each other like an infinite nesting doll of horror. There is another aspect of the stellar population that is rarely discussed in popular sources. Most stars are not alone. The Sun is an exception, not the rule. According to modern estimates, from 50 to 80% of all stars are part of binary or multiple systems. 2, 3, sometimes 4 or more stars bound by gravity, rotating around a common center of mass. This means that the real number of stellar systems is significantly smaller than the number of stars. But it also means that the dynamics of these systems are incredibly complex. Planets in binary systems experience gravitational perturbations from 2 luminaries simultaneously. Their orbits can be stable for billions of years, or they can collapse in a matter of millennia. Life on such planets, if it is possible at all, will develop in conditions radically different from those on Earth. 2 suns in the sky, complex cycles of day and night, unpredictable seasons. Now multiply all this by sextillions. Every star is a potential system. Every system is potential planets. Every planet is potential conditions for something. We cannot even imagine the diversity of worlds existing in the universe. Our imagination is too poor, our experience too limited. Stars are born in giant clouds of gas and dust, called molecular clouds or stellar nurseries. One of the most famous such places is the Orion Nebula, visible to the naked eye as a blurry spot in the constellation Orion. This is a region of active star formation where hundreds of new stars are forming right now. The process begins with gravitational collapse. A small inhomogeneity in a gas cloud, a slightly denser patch, begins to attract surrounding matter. The more matter collects, the stronger the gravity. The stronger the gravity, the more matter is attracted. Positive feedback that turns a scattered cloud into a dense core. As it compresses, the temperature rises. When the center of the protostar reaches about 10 million degrees, thermonuclear fusion starts. The fusion of hydrogen atoms into helium. The star lights up, a new luminary is born. This process takes from several 100,000 to several million years, a moment by cosmic standards, and it happens constantly, everywhere in the universe. Right now, while you hear these words, new stars are being born in thousands of galaxies. Gas clouds are compressing, protostars are heating up, thermonuclear reactions are starting. The universe is not static. It boils with activity that we do not see. But not all clouds give birth to stars in the same way. In some galaxies, star formation has practically stopped. Elliptical galaxies, giant spherical clusters of old reddish stars, almost do not produce new luminaries. All their gas is either spent or heated to temperatures at which collapse is impossible. These galaxies are cemeteries inhabited by ancient stars slowly burning out in anticipation of the end. In other galaxies, on the contrary, star formation occurs at a frantic speed. So-called starburst galaxies produce new stars hundreds of times faster than the Milky Way. They literally burn from within, spending their gas reserves with insane wastefulness. In a few tens of millions of years, they will be exhausted and go out, turning into quiet dead systems. The Tarantula Nebula in the Large Magellanic Cloud is one of the most active star formation regions in our local group of galaxies. If it were in the place of the Orion Nebula, only 1,300 light-years from Earth, it would occupy half the sky and cast shadows on the surface of our planet. Its luminosity is so great that it would be visible during the day. Inside the Tarantula Nebula is the star cluster R136, one of the densest known clusters of young stars. In its center are concentrated dozens of blue giants, each of which is millions of times brighter than the sun. The total luminosity of this cluster is equivalent to 50 million suns. 50 million suns in a volume of only a few light years. But the most striking thing about this cluster is its age, about 1 to 2 million years. By human standards, this is antiquity, but by stellar standards, infancy. The stars in this cluster have only just been born, only just lit up. They have not yet managed to live even 1,000th part of their lives. And here we encounter one of the strangest aspects of astronomy. We observe objects that exist in completely different timescales. A red dwarf can burn for 1 trillion years longer than the universe has existed. A blue giant will burn out in a few million. A human life is 70 to 80 years. This is a moment even compared to the shortest-lived stars. We are like moths trying to understand the life cycle of a sequoia. We see only one frame of a film billions of years long, and based on this single frame, we try to restore the entire plot. Now let us talk about what we do not see, not because it is too far, but because it is hidden. The center of our galaxy, the Milky Way, is at a distance of about 26,000 light-years from us. There is located the supermassive black hole, Sagittarius A, surrounded by an incredibly dense cluster of stars. The density of stars in the center of the galaxy is millions of times higher than in the neighborhood of the Sun. If we lived on a planet near the galactic center, the night sky would be strewn with stars so densely that no dark gaps would remain between them. Night would be bright, like a cloudy day on Earth. But we cannot see these stars directly. Between us and the center of the galaxy lie clouds of cosmic dust, tiny particles scattering and absorbing light. These clouds are opaque to visible radiation. They hide entire regions of the Milky Way from us, creating dark bands in photographs of our galaxy. Only infrared and radio telescopes are able to look through this dust curtain. Infrared radiation passes through the dust almost unhindered, allowing us to see what is hidden from optical instruments. Thanks to infrared astronomy, we learned about the existence of the black hole in the center of the galaxy, about stars rotating around it at crazy speeds, about the structure of the galactic nucleus. But how much more remains hidden? How many stars are hiding behind dust clouds, inaccessible even for infrared telescopes? We know that our counts are not complete. We know that the real number of stars in the galaxy is higher than our estimates. But how much higher remains a mystery. And this applies not only to the center of the galaxy. Interstellar dust is distributed throughout the entire disk of the Milky Way. It concentrates in spiral arms, in star formation regions, around young star clusters. Every dust cloud is a blind spot on our map of the universe, a region about which we can only guess. There is another class of objects about which we know surprisingly little: rogue stars. Stars ejected from their home galaxies and flying through intergalactic space in complete solitude. Such stars are formed in different ways. Sometimes a star finds itself too close to a supermassive black hole in the center of a galaxy. A gravitational maneuver gives it a monstrous speed, sufficient to overcome the gravity of the entire galaxy and fly into the intergalactic void. Such stars are called hypervelocity stars. Their speed can reach 1,000 kilometers per second and more. Other rogue stars are formed during galaxy collisions. When two galaxies merge, their gravitational fields interact chaotically. Millions of stars are ejected to the periphery, losing connection with their native systems. They become wanderers traveling through the cosmic void. According to some estimates, in intergalactic space, there may be as many stars as in all galaxies combined. This means that half of the stellar population of the universe, or even more, is hidden from our eyes in the abyss between galaxies. These stars are too distant and too scattered for us to detect them. They shine into the void, observed by no one, known to no one. When in 2014 the Hubble Space Telescope conducted deep observations of a galactic cluster in the constellation Fornax, astronomers discovered a dim, scattered glow between galaxies. This glow, the so-called intra-cluster light, comes from rogue stars lost by their galaxies. Analysis showed that these wandering stars can make up to 10% of the entire stellar mass of the cluster. 10%. On the scale of a galactic cluster, this is trillions of stars. Trillions of suns drifting in absolute darkness, without planets, without satellites, without any landmarks, just lonely lights in the infinite night. And we are only beginning to understand how common this phenomenon is. Every galactic cluster, every group of galaxies, every supercluster, all of them are surrounded by clouds of lost stars. Stars that will never be included in our counts because we simply do not know how to count them. Another category of invisible luminaries is first-generation stars, the so-called Population 3. These are the first stars formed after the Big Bang, when the universe consisted only of hydrogen, helium, and trace amounts of lithium. No heavy elements, no carbon or oxygen, no metals. These first stars were monsters. According to theoretical calculations, their mass could reach hundreds of solar masses. They burned incredibly brightly and burned out incredibly fast in a few million years. Then they exploded, enriching the universe with heavy elements from which stars of the next generations, planets, were then formed. and ultimately you and I. The problem is that we have never seen population 3 stars directly. They all died long ago. Billions of years have passed since their disappearance. We can only look for their traces. Chemical signatures in ancient second-generation stars, weak bursts in cosmic background radiation, theoretical models and simulations. This means that an entire era of stellar history, the very first and most important, remains invisible to us. We know that these stars existed. We know that without them there would be neither us, nor our planet, nor our sun. But to see them is impossible. And so we come to the inevitable admission. Science does not know how many stars exist in the universe. It does not know approximately, it does not know to within an order of magnitude. All our estimates are guesses based on incomplete data, limited observations, and bold extrapolations. We do not see most stars. Red dwarfs are too dim, rogue stars are too distant and scattered. Dust hides entire regions of galaxies. Distant galaxies are inaccessible to our telescopes. First stars died long ago, and the universe beyond the horizon of observability is a complete terra incognita about which we cannot say anything definite. We are like blind men feeling an elephant. One felt the trunk and thinks the elephant is like a snake. Another felt the leg and thinks the elephant is like a column. A third felt the ear and thinks the elephant is a fan. We feel the universe with our weak instruments and think we understand it, but we do not. We only build models that correspond to that tiny part of reality that we were able to reach. And this admission is not a weakness of science. It is its honesty. A real scientist does not pretend to know more than he knows. He recognizes the boundaries of his knowledge and works on expanding them. But some boundaries may be insurmountable. Some questions may forever remain without an answer. How many stars are in the universe we do not know, and probably will never know exactly. But what we do know is already enough to change our idea of our own place in space. What we can see is already terrifying enough. Let us talk about specific stars. Not about categories and classifications, but about real objects with names and coordinates, about luminaries that astronomers have studied for decades, about which thousands of scientific articles have been written and which still remain mysteries. Betelgeuse, a red supergiant in the constellation Orion, one of the brightest stars of the night sky. Its name comes from Arabic and means the armpit of the hunter. That is exactly where it is located on the celestial figure of Orion. Betelgeuse is at a distance of approximately 700 light-years from Earth, although the exact value is still being refined. This star is dying. It has already exhausted the hydrogen in its core, passed through the helium-burning stage, and is now burning heavier elements. Its outer layers have swollen to monstrous sizes. If Betelgeuse were placed in the position of the Sun, its surface would reach the orbit of Jupiter. But this hugeness is a sign of agony, not strength. The star is preparing for death. At the end of 2019, something strange happened. Betelgeuse dimmed sharply. Its brightness fell by more than 2 times, and astronomers all over the world held their breath. Is this it? Will we witness a supernova explosion in real time? No. It turned out that the cause of the dimming was a giant cloud of dust ejected by the star itself and partially blocking it from us. But this episode reminded us of the inevitable. Betelgeuse will explode. This could happen tomorrow, in 1,000 years, or in 100,000 years. By cosmic standards, it is already on the edge. And when this happens, an object brighter than the full moon will appear in the Earth's sky, visible even during the day, a sight that humanity has never observed in recorded history. Another star is Eta Carinae. It is located in the southern hemisphere of the sky at a distance of about 7,500 light-years. This is one of the most massive and unstable stars known to science. Its mass exceeds the solar mass by 100 to 150 times, its luminosity by 5 million times. In 1843, Eta Carinae experienced the so-called Great Eruption. For a short time, it became the second brightest star in the sky, yielding only to Sirius. Astronomers of that time did not understand what was happening. Today we know that the star ejected a huge amount of matter, about 10 to 20 solar masses, forming the Homunculus Nebula, visible in modern telescopes. But Eta Carinae did not explode then. It still exists, lurking inside the nebula it created. It is unstable, it is unpredictable, and it can turn into a hypernova, an explosion dozens of times more powerful than an ordinary supernova at any moment. Scientists do not know when. Maybe in a million years. Maybe while you hear these words. There is a star called Tabby, an unofficial name given in honor of the astronomer Tabitha Boyajian, who was the first to draw attention to its oddities. Official designation KIC 8462852. It is located in the constellation Cygnus, about 1,470 light-years from us. This star demonstrates absolutely inexplicable fluctuations in brightness. Ordinary stars, of course, change brightness due to spots on the surface, due to planets passing in front of them, due to eclipses in binary systems. But the fluctuations of Tabby's star do not fit into any known model. Its brightness falls irregularly, sometimes by fractions of a percent, sometimes by almost 22%. This is a huge value. For comparison, a transit of Jupiter in front of the Sun would cause a fall in brightness of less than 1%. Whatever blocked Tabby's star, it must be giant and asymmetric and non-periodic. Among the proposed explanations are a swarm of comets, a dust cloud, even an alien megastructure like a Dyson sphere. The latter hypothesis is almost certainly wrong. Analysis of the spectrum shows that the darkening is caused by fine dust, not solid objects. But even the dust explanation generates new questions. Where does this dust come from? Why does it behave so strangely? Why do we not see anything similar in other stars? Tabby's star reminds us of how little we know. Every star is a riddle. Every glowing dot in the sky hides a story that we are only beginning to read. And now let us talk about pulsars, objects that should not exist from the point of view of common sense, but exist despite everything. A pulsar is what remains after the death of a massive star. When a star with a mass from 8 to about 25 solar masses exhausts its nuclear fuel, its core collapses under the action of gravity. Electrons are pressed into protons, forming neutrons. Matter is compressed to an unimaginable density, billions of tons in a cubic centimeter. A neutron star is formed. A neutron star is an object with a mass 1.5 to 2 times more than the Sun, compressed to the size of a city. The diameter of a typical neutron star is about 20 kilometers across. This distance can be driven in a car in 15 minutes. And yet inside this tiny ball is enclosed a mass exceeding the solar mass. Gravity on the surface of a neutron star is 300 billion times stronger than on the surface of the Earth. If you could stand on a neutron star, and you could not, you would be instantly crushed. Your weight would be about 20 trillion tons. Even light passing near a neutron star is noticeably bent by its gravity. When a star collapses into a neutron star, the law of conservation of angular momentum acts. The same law that makes a figure skater rotate faster when she presses her arms to her body. The original star rotated slowly, performing one revolution in days or weeks, but after compression, millions of times its rotation accelerates millions of times. Some neutron stars perform hundreds of revolutions per second. Think about this. An object with a mass greater than the Sun rotates around its axis several hundred times every second. This is on the edge of the physically possible. Pulsars got their name because they radiate narrow beams of radio waves, like lighthouses. Due to rotation, these beams are periodically directed toward Earth, creating regular pulses. The first pulsar was discovered in 1967 by the British astronomer Jocelyn Bell Burnell. The signal was so regular that at first researchers half-jokingly called it LGM-1, Little Green Men. They did not believe that nature was capable of creating such an exact mechanism, but nature created many. Today, more than 3,000 pulsars are known in our galaxy alone. According to estimates, in the Milky Way there may exist about 1 billion neutron stars, the dead remains of massive stars that ceased to exist over billions of years of the galaxy's history. There is a special category of neutron stars that are scarier than ordinary pulsars. They are called magnetars. These are neutron stars with an unimaginably powerful magnetic field, 1 quadrillion times stronger than Earth's. A quadrillion is a 1 with 15 zeros. The magnetic field of a magnetar is so intense that it distorts the structure of atoms. Normally, atoms have a spherical shape. Electrons rotate around the nucleus in all directions. But in the field of a magnetar, electrons are forced to move only along the field lines, and the atoms become elongated, cigar-shaped. Chemistry in such conditions works completely differently. Matter takes forms that exist nowhere else in the universe. Magnetars are unstable. Their crust, a thin layer of relatively normal matter on the surface of the neutron core, periodically cracks under the pressure of monstrous magnetic forces. These starquakes release a colossal amount of energy in the form of gamma-ray bursts. One such burst in a fraction of a second radiates more energy than the sun in 100,000 years. On December 27, 2004, the magnetar SGR 180620, located 50,000 light-years from Earth on the other side of the galaxy, experienced such a flare. Gamma radiation reached our planet and ionized the upper layers of the atmosphere, disrupting radio communication on the sunlit side of the Earth. This happened despite the colossal distance and despite the fact that we were to the side of the main direction of the ejection. Think about this. An event at a distance of 50,000 light-years affected our daily life. A star that died long before the appearance of humanity is still capable of reaching us through the abyss of space and time. And there are billions of such objects in the universe. Billions of dead stars turned into pulsars and magnetars. Billions of cosmic lighthouses and time bombs. But neutron stars are not yet the scariest. There are worse objects. There are stars that are so massive that even neutron degeneracy cannot stop their collapse. Their cores continue to compress until the entire mass is concentrated in one point of singularity. A black hole is formed. Но о черных дырах мы поговорим позже. Now let us focus on what happens with stars during life, on the processes that make them so dangerous. Every star is a battlefield. Inside it, a war is constantly going on between two forces: gravity, striving to compress the star into a point, and radiation pressure, striving to tear it into pieces. As long as these forces are in balance, the star is stable, but the balance is fragile, and its disruption leads to disaster. The sun ejects into space a constant stream of charged particles, the so-called solar wind. Every second, the sun loses about 1.5 million tons of matter in the form of this wind. Sounds like a lot, but compared to the total mass of the sun, it is negligible. In its entire life, the sun will lose less than 1/1000th of its mass with the wind. Но для более массивных звезд ситуация иная. Blue giants, which I mentioned earlier, have stellar winds millions of times more intense than the solar one. They literally blow themselves away into space. Some of them lose a mass equivalent to the Earth every year. They are surrounded by expanding shells of discarded matter, nebulae that will glow long after the death of the star that gave birth to them. A Wolf-Rayet star, a special class of massive stars in the late stages of evolution, can lose mass at a rate equivalent to one solar mass in 100,000 years. This means that in several million years of its short life, such a star will discard a significant part of what it was born with. It is like a candle in the wind, burning at both ends. And this discarded matter does not disappear without a trace. It flies away at a speed of thousands of kilometers per second, colliding with the interstellar medium, heating it, ionizing it, creating shock waves that spread for tens of light years. One star is capable of transforming an entire region of a galaxy with its wind even before it explodes as a supernova. But winds are a constant, relatively calm process. There are events much more dramatic. Stars are unstable, especially massive ones, especially young ones, and especially old ones. They pulsate, expanding and contracting with periods from hours to years. They flare up, suddenly increasing brightness by dozens of times. They eject monstrous prominences into space. Arches of incandescent gas millions of kilometers high, solar flares, powerful explosive events on our sun release energy equivalent to billions of megaton bombs. They eject clouds of plasma into space that reach Earth in 1 to 3 days and cause geomagnetic storms. Aurorae, disruptions in radio communication, damage to satellites, even failure of power grids. All these are consequences of solar flares. In 1859, the so-called Carrington event occurred, the most powerful geomagnetic storm in recorded history. Telegraph systems all over the world failed. Operators received electric shocks. Some telegraph machines continued to work even after disconnection from power sources. They were powered by induced currents. Aurorae were observed even in the tropics. If an event of such scale happened today, the consequences would be catastrophic. Our civilization depends on electricity, on satellites, on electronics. A powerful geomagnetic storm is capable of destroying a significant part of this infrastructure in a matter of hours. Economic damage is estimated in trillions of dollars. Recovery will take years. And this is only our sun, a calm, stable star of the middle class. Other stars flare up thousands of times stronger. UV Ceti-type stars, small red dwarfs, are known for their monstrous flares, which for a short time increase their brightness hundreds of times. A planet near such a star will be periodically sterilized by ultraviolet radiation. Any life on its surface will be destroyed again and again. And such stars are the majority. Red dwarfs, making up about 70% of all stars, are almost all flare stars. They are active, unstable, dangerous. Dreams that their long-lived planets can be home for life break against reality. These worlds are under constant bombardment by radiation. We move to the next level of violence. When two neutron stars in a binary system gradually approach each other, radiating gravitational waves and losing orbital energy, they finally collide. This event is called a kilonova. It happens incredibly fast, in milliseconds, but releases energy comparable to billions of ordinary stars. On August 17, 2017, the LIGO and Virgo detectors recorded gravitational waves from the merger of two neutron stars in the galaxy NGC 4993 at a distance of about 130 million light-years. This was the first observation of such an event in the gravitational and electromagnetic ranges simultaneously. Analysis showed something important. At the moment of the collision of neutron stars, heavy elements are formed: gold, platinum, uranium. Most of these elements in the universe are born exactly like this, not in the depths of ordinary stars, but in the cataclysms of merging neutron stars. The gold ring on your finger, if you have one, was created at the moment of the death of two dead stars billions of years ago, long before the formation of the solar system. Kilonovae are rare events. In a typical galaxy, they happen once every few thousand or tens of thousands of years. But in the universe, there are billions of galaxies. Somewhere right now, in this very moment, two neutron stars are colliding, generating a flash of light brighter than a billion suns and clouds of newly born heavy elements. We exist thanks to violence. The atoms in our bodies were created in the thermonuclear reactors of stars, ejected into space by supernova explosions, enriched with products of the merger of neutron stars. We are children of disasters. Our flesh is woven from the debris of dead worlds. And this is only the beginning of the talk about violence of cosmic scales. What happens with individual stars is only a prelude to what happens at the level of the galaxy and the universe as a whole. Supernova. We hear this word often, but rarely think about what it means in reality. Not metaphorically, not poetically, but literally physically in numbers and energies. When a massive star exhausts its reserves of nuclear fuel, its core stops producing energy that supports the outer layers. In a fraction of a second, not in minutes, not in hours, but in a fraction of a second, the core collapses. The outer layers, deprived of support, collapse inward at a speed of tens of thousands of kilometers per second. They hit the compressed core and bounce back, generating a shock wave that tears the star from within. In a few seconds, energy is released that the sun produces in 10 billion years. 10 billion years of solar radiation in seconds. This number is so absurd that it is impossible to comprehend. One can only write it down and move on, resigned to one's own inability to understand. But here is what is important. Most of this energy, about 99%, is carried away by neutrinos. These ghostly particles almost do not interact with matter. They permeate everything on their path, planets, stars, galaxies, not noticing obstacles. At the moment of a supernova explosion, so many neutrinos fly out of it that even at a distance of thousands of light years, their stream through every square centimeter is calculated in trillions. On February 23, 1987, an event occurred that changed astronomy forever. In the Large Magellanic Cloud, a dwarf galaxy satellite of the Milky Way, at a distance of about 168,000 light-years, a supernova exploded. It received the designation SN 1987A and became the first supernova visible to the naked eye since 1604. Several hours before telescopes recorded the optical flare, neutrino detectors in Japan, the USA, and the USSR simultaneously registered a burst. About 25 neutrinos in 13 seconds, 25 particles. This seems a vanishingly small number, but these were neutrinos from the collapse of the core of a star in another galaxy. The fact of their registration in itself was a triumph of science and technology. SN 1987. Confirmed our theories about the mechanism of supernova explosions. It showed that we understand the physics of these processes, at least in general terms. But it also reminded us of how close death can get. 168,000 light-years. This is far by human standards, but by galactic standards, it is the next yard. If a supernova of such power exploded within 50 light-years from Earth, the consequences would be catastrophic. The ozone layer would be destroyed by gamma radiation and cosmic rays. Ultraviolet would reach the surface unhindered, sterilizing land and upper layers of the ocean. Mass extinction would be inevitable. And in a radius of 50 light-years from us, there are about 1,300 stars. Most of them are calm red and orange dwarfs, incapable of a supernova explosion. But there are also more massive stars whose fate is not yet determined. IK Pegasi is a binary system at a distance of about 150 light-years. It consists of an ordinary Class A star and a white dwarf. The white dwarf gradually pulls matter from its companion, increasing its own mass. When its mass reaches the Chandrasekhar limit, approximately 1 4/10 solar masses, it will explode as a Type 1, a supernova. This will not happen soon, in millions of years, but it will happen. There is a classification of supernovae based on their spectra and mechanisms of explosion. Type 1a is a thermonuclear explosion of a white dwarf that has gained critical mass. Types 1b, 1c, and 2. This is the collapse of the core of massive stars, differing in the composition of the outer shells. But there are events that exceed ordinary supernovae in power by dozens and hundreds of times. They are called hypernovae. A hypernova is not just a large supernova, it is a qualitatively different phenomenon. It happens when the core of an especially massive and rapidly rotating star collapses not into a neutron star, but directly into a black hole. In this process, two narrow jets are formed, streams of relativistic plasma breaking out along the axis of rotation at a speed close to the speed of light. If one of these jets is directed toward Earth, we see a gamma-ray burst, a short-term flash of hard radiation of monstrous intensity. Long gamma-ray bursts, lasting from several seconds to several minutes, are precisely associated with hypernovae. On December 9th, 1997, orbital detectors recorded gamma-ray burst GRB 971214. Its redshift indicated a distance of about 12 billion light-years, almost at the edge of the observable universe. Calculations showed that in several seconds, this object radiated energy equivalent to the conversion of several solar masses into pure radiation. Several suns, completely converted into light in seconds. Later, it turned out that the energy was greatly overestimated. The radiation was directional, focused in a narrow beam, so the total energy turned out to be less. But even taking this into account, gamma-ray bursts remain the most energetic events in the universe after the Big Bang. On March 19, 2008, gamma-ray burst GRB 080319b occurred at a distance of about 7.5 billion light-years. Its optical afterglow reached a visible magnitude of 5 3/10. That is, it was visible to the naked eye for about 30 seconds. An object at the distance of half the observable universe was visible without a telescope. This is the most distant object ever observed by the human eye directly. Now imagine that a similar gamma-ray burst occurs in our galaxy and is directed toward Earth. At a distance of several thousand light-years, it will destroy all life on the planet instantly. The atmosphere will not save. Gamma radiation will pierce it right through. The night side of the planet will receive a dose from secondary radiation, the decay of atmospheric molecules. There will be no survivors. Some researchers link the mass Ordovician-Silurian extinction, the second in scale in the history of the Earth, which occurred about 445 million years ago, with a possible gamma-ray burst in relative proximity to the solar system. There are no direct proofs, but indirect signs: sharp cooling, destruction of the ozone layer, extinction mainly of marine organisms of the upper layers of water agree with such a hypothesis. We live in a shooting range. Bullets fly past us constantly. It is just that so far not one has hit. But individual stars are only part of the picture. Let us rise to the next level and look at violence of galactic scales. Galaxies are not static. They move, interact, collide. Our Milky Way is bound by gravity to dozens of dwarf satellite galaxies, some of which it is gradually swallowing. Right now, the Milky Way is tearing apart the Sagittarius dwarf spheroidal galaxy. The stream of its stars has stretched across the entire sky, forming a giant arch around our galaxy. But these are small collisions. There are events much more grandiose. The Andromeda Galaxy, the closest large galaxy to us, is at a distance of about 2.5 million light-years. It contains approximately 1 trillion stars, several times more than the Milky Way, and it is approaching us at a speed of about 110 kilometers per second. In approximately 4.5 billion years, Andromeda and the Milky Way will collide. This is not an exaggeration, not a metaphor. This is a forecast based on measurements of speeds and trajectories. Two galaxies will pass through each other. Their gravitational fields will deform both systems, pulling long tidal tails out of them. Then they will diverge, slow down, turn around, and come together again. This dance will repeat several times until both galaxies merge into one giant elliptical system, which has already been dubbed Milkomeda. Paradoxically, during a galaxy collision, direct collisions of stars are extremely unlikely. The distances between stars are so great compared to their sizes that two galaxies pass through each other almost unhindered. It is like two swarms of bees flying toward each other. Individual bees rarely collide, although the swarms mix. But the gravitational effects will be colossal. The orbits of stars will change. Some will be ejected into intergalactic space, becoming those very rogue stars. Others will fall toward the centers of the galaxies, providing supermassive black holes with fresh fuel. Gas clouds will collide and give birth to a wave of star formation. Billions of new stars will light up almost simultaneously. The Hubble telescope has observed many galaxies in the process of collision. The antennae galaxies, two spiral systems that began to merge about 600 million years ago. Their distorted forms, elongated tails, bright nodes of newborn stars. All this is a harbinger of what awaits us in billions of years. The mice galaxies, another merging pair with characteristic long tidal tails. Stephan's quintet, a group of 5 galaxies, 4 of which are in the process of gravitational interaction. These images are beautiful. They adorn book covers and computer screens. Но мы забываем, что смотрим на катастрофы, на события, в которых миллиарды звезд теряют свои планетные системы, в которых целые миры, возможно, обитаемые, выбрасываются в ледяную пустоту межгалактического пространства. In the center of every large galaxy is a supermassive black hole. The mass of such objects varies from millions to tens of billions of solar masses. The black hole in the center of the Milky Way. Sagittarius A has a mass of about 4 million suns. The black hole in the center of the galaxy M87, which was photographed for the first time in 2019, has a mass of about 6.5 billion suns. When galaxies merge, their central black holes also ultimately approach and merge. This process takes hundreds of millions of years. First, the black holes approach thanks to dynamical friction, interaction with surrounding stars. Then, when they are close enough to each other, they begin to radiate gravitational waves and rapidly converge. The final merger happens in fractions of a second. Two black holes merge into one, more massive, and the excess energy is carried away by gravitational waves. The merger of supermassive black holes is one of the most powerful events in the universe. Gravitational waves from such mergers propagate throughout the entire cosmos, causing microscopic oscillations of space-time that can theoretically be fixed. The LISA project, a space gravitational wave observatory whose launch is planned for the 30s, should detect signals from merging supermassive black holes throughout the entire observable universe. But black holes are dangerous not only during a merger, they are dangerous constantly. When matter falls onto a black hole, it does not fall right away beyond the event horizon. First, it forms an accretion disk, a flat spiral structure rotating around the black hole. Friction in the disk heats the matter to millions of degrees. It begins to radiate in the X-ray and ultraviolet ranges with monstrous intensity. An actively feeding supermassive black hole is called an active galactic nucleus. The brightest of them, quasars, radiate energy equivalent to trillions of suns. One quasar is capable of shining brighter than the whole galaxy in which it is located. It is not the black hole itself that shines. Light cannot escape from beyond the event horizon. It is the incandescent matter falling inside that shines. Quasar 3, C273 in the constellation Virgo. The first identified quasar, discovered in 1963, is at a distance of about 2.5 billion light-years. Despite this, it is visible in amateur telescopes as a star of the 13th magnitude. Its luminosity exceeds the luminosity of 4 trillion suns. Many quasars eject relativistic jets, streams of plasma accelerated to speeds close to the speed of light. These jets stretch for hundreds of thousands of light-years, piercing the entire galaxy and going far beyond its limits. The energy enclosed in these streams is unimaginable. They are capable of heating and ionizing intergalactic gas at distances of millions of light-years. quasar APM 08279 plus 5255, one of the brightest known objects in the universe. It is at a distance of about 12 billion light-years. It radiates energy equivalent to hundreds of trillions of suns. The black hole in its center has a mass of about 20 billion solar masses and consumes matter at a rate of about 1,000 solar masses per year. 1,000 suns fall into a black hole and disappear forever every year. But quasars are a phenomenon of the distant past. The peak of their activity fell on the era when the universe was 2 to 3 billion years old. Then the galaxies were young, there was a lot of gas, black holes were actively feeding. Today, most supermassive black holes are in a dormant state, like Sagittarius A in the center of our galaxy. They consume only accidental stars and gas clouds that incautiously approach too close, but this calm is deceptive. In 2011, astronomers fixed an unusual flare from the center of a distant galaxy at a distance of about 4 billion light-years. Analysis showed that a supermassive black hole tore apart a star passing by with tidal forces. The star was literally stretched into a thread, part of which fell onto the black hole, generating a flare visible through half the universe. Such events, tidal disruptions, happen once every few thousand years in a typical galaxy. But there are trillions of galaxies. On the scale of the universe, every second some star is torn to pieces by a black hole. Every second somewhere a sun dies, not in a majestic supernova explosion, but in a silent but no less cruel tidal disruption. There is another category of objects worth mentioning: blazars. These are quasars whose jets are directed almost exactly at Earth. We are looking straight into the barrel of a cosmic gun. Blazar Markarian 421 in the constellation Ursa Major, one of the closest to us, at a distance of about 400 million light-years. It emits high-energy gamma radiation that reaches Earth's detectors. Periodically, its brightness increases sharply. The jet becomes unstable, ejecting clumps of plasma that collide with each other and radiate even more intensely. We are in relative safety from Markarian 421. It is too far to cause us harm. But imagine a galaxy located several thousand light-years from an active quasar that has directed its jet at it. Every planet in this galaxy that finds itself in the path of the stream will be sterilized, possibly destroyed completely. The atmosphere stripped away, the oceans evaporated, the surface melted. And such situations in the universe are an infinite number. Right now, millions of worlds are dying under the strikes of quasars, gamma-ray bursts of supernovae, worlds of whose existence we will never know, civilizations, if they were there, that disappeared without a trace, without memory, without hope that someone will remember them. The cosmos is not cruel. Cruelty implies intent. The cosmos is simply indifferent. It does not notice us, does not know about our existence, is not interested in our fate. It simply exists. And in its existence are enclosed forces of such a scale that our survival is a statistical accident. We survived not because we deserved it, not because we were chosen, not because the universe is benevolent to life. We survived because we were lucky, because the bullets have flown past for now, because gamma-ray bursts were not directed at Earth, because supernovae exploded far enough away, because the sun turned out to be a stable star in a quiet corner of the galaxy. But luck does not last forever, and here is what remains a mystery. Why are we here at all, in a world where violence is the norm, where stars are born and die by the billions, where galaxies collide and swallow each other? How did life arise? How did it hold out long enough so that we could ask this question? There is no answer. There is only the silence of space and the light of distant stars, each of which can be both a cradle of life and an instrument of its destruction. We have already spent considerable time immersing ourselves in numbers, scales, and cataclysms. We talked about sextillions of stars, about supernovae and gamma-ray bursts, about galaxy collisions and black holes devouring matter. But now the time has come to ask the question that actually matters. What does all this mean for us? For you, listening to these words in the darkness of your room, for humanity as a whole, for the very idea of life and reason in the universe. Because numbers are just numbers. They mean nothing by themselves. Meaning appears only when we try to comprehend these numbers, relate them to our existence, to our hopes and fears. Let us start with the simplest and most painful question. How significant are we? Earth is a planet with a diameter of about 12,756 kilometers. It rotates around the Sun at a distance of about 150 million kilometers. The Sun is a medium-sized star, one of hundreds of billions in our galaxy. A galaxy is one of trillions in the observable universe, and the observable universe is, possibly, only a tiny part of all that exists. If we imagine the entire observable universe in the form of an ocean, then Earth will be not even a drop of water. It will be a hydrogen atom in this drop. Not even an atom, but a subatomic particle. Not even a particle, but a quantum fluctuation existing for a fraction of a moment. We are used to thinking of ourselves as the center of the universe. For millennia, people believed that Earth was in the center of the universe, that the sun and stars rotated around us. Copernicus destroyed this illusion, showing that Earth rotates around the sun. But this was only the beginning. Then we learned that the sun is not the center of the universe, but an ordinary star on the periphery of a galaxy. Then, that our galaxy is not unique, that there are billions of such galaxies. Then, that the universe itself arose in a big bang and is constantly expanding. Every discovery pushed us further and further from the center, deeper and deeper to the roadside. Today we know that there is no center. The universe expands uniformly in all directions, and every point in it can consider itself the center, which is equivalent to there being no center at all. We are not in the center, we are nowhere or everywhere, which is the same thing. This is called the Copernican principle, the idea that humanity does not occupy a privileged position in the universe. We are not special. We are not chosen. We are an accident that arose on an unremarkable planet, at an unremarkable star, in an unremarkable galaxy. But here is the paradox. If we are not special, if the conditions on Earth are not unique, if there are sextillions of stars, why do we not see others? Why is the cosmos silent? This question is known as the Fermi paradox, after the physicist Enrico Fermi, who first formulated it in 1950. The essence is simple. If a huge number of stars exist in the universe, and many of them have planets, and life could arise on some of these planets, and part of this life could develop to the level of a civilization, then where is everything? Why do we not receive their signals? Why did they not fly to us? Why is the sky not teeming with traces of alien activity? Let us count. Our galaxy has existed for about 13 billion years. Even if a technological civilization spreads very slowly, say, at a speed of 1% of the speed of light, it could colonize the entire galaxy in about 10 million years. This is a moment compared to the age of the galaxy. If at least one civilization arose a few million years before us, and given the number of stars, this is practically inevitable, it should have already filled the galaxy. But we see no signs of this. The silence of space is not just an absence of an answer. It is an answer in itself, and it is frightening. There exist many attempts to explain the Fermi paradox. Let us consider some of them and think about what each explanation means for us. The first explanation: we are alone. Life is an incredibly rare phenomenon, and intelligent life is even rarer. Possibly, we are the only technological civilization in the galaxy, or even in the observable universe. This explanation flutters our self-esteem, but it requires incredible coincidences. We must be not just rare, but unique, the only ones among sextillions of stars. Statistically, this seems unlikely, but statistics do not guarantee a result. Possibly, we really won the cosmic lottery. If this is true, our responsibility is unimaginable. We are the only carriers of reason in the universe, the only ones capable of understanding space, appreciating its beauty, asking questions about its nature. If we destroy ourselves in a nuclear war, a climate disaster, a pandemic, the universe will lose the only reason it had. It will again become blind, deaf, meaningless. Just matter and energy moving according to the laws of physics, without a witness, without understanding, without meaning. The second explanation, life is common, but reason is a rarity. Bacteria, plants, even animals may exist on many planets, but reason, the ability for abstract thinking, technology of civilization, arises extremely rarely. We are an exception, not the rule. On Earth, life has existed for about 4 billion years, but technological civilization less than 10,000 years. This means that life has spent 99 and 997 ten-thousandths% of its history without reason in our understanding. Dinosaurs dominated the planet for 160 million years and did not build a single telescope. Reason is not an inevitable result of evolution. It is an accident, a byproduct, an evolutionary experiment that might never have happened. If this is true, the universe may be full of life, but dead in terms of reason. Oceans under the ice crusts of satellites, forests on planets of distant stars, ecosystems of unimaginable complexity, and not a single creature capable of looking at the stars and asking what is there. We may be the only ones who ask questions, the only ones who look for answers. The third explanation, civilizations destroy themselves. They arise, develop technologies, and then perish from their own weapons, from ecological disasters, from internal conflicts. No one lives to the stage of interstellar expansion. This is the most frightening explanation. It assumes the existence of the so-called Great Filter, a certain barrier that not a single civilization is able to overcome. If the filter is in our past, for example, at the stage of the emergence of life or eukaryotes, we are lucky, we have already passed it. But if the filter is in our future, the same fate awaits us as all the others. Look at our history. Nuclear weapons capable of destroying civilization in hours. Climate changes threatening the foundations of our existence. Biotechnology opening possibilities for creating deadly pathogens. Artificial intelligence whose consequences we cannot even predict. We are a civilization of teenagers playing with matches in a powder magazine. If every civilization goes through this stage, and most do not survive, the silence of space takes on a sinister meaning. This is not just emptiness, it is a cemetery. Billions of perished civilizations whose ruins are scattered through the galaxy, invisible to us. The fourth explanation. They are here, but we do not see them. A developed civilization can use technologies that we are unable to detect. Or they intentionally hide, or they observe us without interfering, as scientists observe an anthill. This hypothesis is known as the zoo hypothesis. We are a reserve fenced off by an invisible fence. Aliens know about us but prefer not to enter into contact. Possibly, so as not to affect our development. Possibly, because we are not interesting to them. Possibly, for reasons that we are unable to understand. There is a variation of this hypothesis, the dark forest hypothesis. The universe is a forest full of hunters. Any civilization that reveals itself risks being destroyed by a superior opponent. Therefore, everyone is silent, everyone hides, everyone is afraid. If this is true, our attempts to contact aliens, the SETI programs, messages on the Voyager probes, radio broadcasts into space, can be deadly dangerous. We scream into a dark forest, not knowing who will hear us, and the answer may come not in the form of a friendly greeting, but in the form of a sterilizing strike from a distance of thousands of light years. The fifth explanation. The universe is too young. Possibly, we are among the first. Intelligent life is only beginning to appear, and we are among the pioneers. In billions of years, the galaxy will be full of civilizations, but now we are almost alone. This explanation has a certain logic. The early universe was inhospitable for life. There were few heavy elements of carbon, oxygen, iron. They are formed in the depths of stars and during supernova explosions, and their concentration in the interstellar medium grew gradually. The first planets suitable for life could appear only several billion years after the Big Bang. But even taking this into account, enough time has passed. The age of the universe is about 13,800,000,000 years. Earth has existed for 4.5 billion. If other civilizations arose a billion years before us, and this is quite possible, they should have already settled through the galaxy. Silence remains unexplained. Each of these explanations has its problems. Not one is completely convincing, and this in itself is disturbing. We do not know why we are alone. We do not know if we are indeed alone. We ask a question into the void and receive in response only the echo of our own voice. But let us distract ourselves from the question about other civilizations and look at our own fate. What awaits us in the future? What will happen with the Earth, with the Sun, with the galaxy, with the universe? The Sun is a stable star, but even stability has limits. In about 1 billion years, the luminosity of the Sun will increase so much that the oceans of the Earth will begin to evaporate, the greenhouse effect will strengthen, the surface temperature will become incompatible with life. Earth will turn into a likeness of Venus, a parched, waterless hell under a dense atmosphere of carbon dioxide. In 5 billion years, the Sun will exhaust the hydrogen in its core and begin to expand, turning into a red giant. Its outer layers will swallow Mercury, Venus, possibly Earth. Even if Earth avoids being swallowed, and some models predict that the expanding Sun will push its orbit back, it will still be scorched to the ground. The oceans will evaporate, the atmosphere will fly into space, only parched stone will remain. Then the Sun will discard the outer layer, forming a planetary nebula, and its core will compress into a white dwarf, an object the size of the Earth, but with a mass half the solar mass. The white dwarf will slowly cool for trillions of years until it turns into a black dwarf, a cold, dark, dead ball of degenerate matter. Humanity, if it lives that long, must leave Earth long before that, resettle on other planets, in other stellar systems, possibly in other galaxies, become a cosmic civilization or perish. But even a cosmic civilization is not eternal. The universe is aging. Stars are born less and less often because interstellar gas is being exhausted. In 1 trillion years, the last stars will burn out. Galaxies will plunge into darkness, illuminated only by the dim glow of white dwarfs. In 10 to the 37th power years, a number with 37 zeros. Even protons will decay, if modern theories are correct. Matter in the usual sense will cease to exist. Only black holes will remain, slowly evaporating through Hawking radiation. In 10 to the 106th power years, the last black hole will evaporate. The universe will reach heat death, a state of maximum entropy in which nothing happens and nothing can happen. An eternal, unchanging dead void. This is the fate of everything. Of every star, of every galaxy, of every civilization that ever existed or will exist. All roads lead to one end, to a cold, dark eternity. Is it possible to find consolation in this knowledge? Is it possible to reconcile with absolute meaninglessness? Some philosophers claim that yes, that precisely finiteness gives meaning, that a rose is beautiful exactly because it withers, that life is valuable exactly because it is short, that a universe existing eternally without changes would be meaningless. But a universe that is born, lives and dies, gains tragic greatness. Other philosophers object. They say that finiteness does not create meaning, it destroys it, that everything we do, all our achievements, all our sufferings and joys, all this will be forgotten when the last star goes out. What are we building? Castles made of sand on the shore of eternity, and the tide inevitably will wash them away without a trace. Who is right? No one knows. This is a question not of science, but of faith, or its absence. But there is another aspect that is rarely discussed. The very existence of reason, of our reason, is something amazing. The universe gave birth to beings capable of understanding it. Atoms formed in the depths of stars gathered in configurations capable of asking questions about the stars. The cosmos looks at itself with our eyes. This is not a religious statement, it is a statement of fact. We are a part of the universe realizing itself. We are the way in which the cosmos knows itself. And in this, there is some strange greatness that is not canceled either by our smallness or by the inevitability of the end. Carl Sagan said, "We are made of star stuff." This is the literal truth. The carbon in our cells, the iron in our blood, the calcium in our bones. All this was created in thermonuclear reactions inside stars, ejected into space upon their death, gathered into new stars and planets, and ultimately into us. We are descendants of stars, their heirs, their continuation, and possibly only possibly. In this there is some sense, not a divine design, not a predetermined goal, but simply the beauty of accident, the beauty of that from chaos order arises, that from dead matter life arises, that from life reason arises. That reason is capable of looking back and understanding its history. We may be the only ones who do this, or one of many. We may be doomed to perish in 1,000 years or exist for billions. We may never meet other intelligent beings or discover them tomorrow. All this is unknown. But one thing is known for sure. Right now, in this moment, we exist. We think, we feel, we ask questions. And this in itself is a miracle. Not a supernatural miracle, but a natural miracle of nature, a miracle of physics and chemistry, a miracle of evolution and time. Sextillions of stars burn in the abyss. Most of them will never be seen by a single intelligent being. Their light flies through the void for millions of years and dissipates into nothing. But some rays reach eyes, our eyes, and we look up and wonder and ask, what is there? The very fact that we ask is already an answer to a question that the universe possibly never asked, but which we ask for it. And in this question is our significance, not in scales, not in longevity, not in power, but in the ability to ask, in the ability to wonder, in the ability to look at the stars and understand that they are our ancestors. But one question remains for which there is no answer. One question that haunts everyone who seriously thinks about the cosmos. If the universe is infinite, and it may be infinite, then everything that is possible exists in it. Every possible combination of atoms, every possible planet, every possible form of life, every possible civilization, even if you believe quantum mechanics, every possible version of you reading these words. Infinity is not just a large number, it is the absence of boundaries. In an infinite universe, everything that is not forbidden by the laws of physics exists somewhere. It necessarily exists in an infinite number of copies. And then the question arises, what does uniqueness mean? What does significance mean? If an infinite number of planets exist similar to Earth, an infinite number of civilizations similar to ours, an infinite number of beings similar to you, does exactly this Earth, exactly this civilization, exactly you have meaning? There is no answer. There is only silence. Silence between the stars.